Suppose that we wanted to find the volume underneath a surface given by the function z equals f of x, y. Well, one way that we can accomplish this is to take our domain, in this case from 0 to 2 in both x and y, and to chop it up into small rectangles. And these rectangles will have a length of delta x and a width of delta y. And then we could draw rectangular prisms that go up to the height of the function at some point within that rectangle. And the idea would be that these rectangular prisms that I've drawn, like so, would approximate the volume underneath the surface within this small rectangle of area delta x, delta y. So what I would do then is think about, I'm going to slice my domain from 0 to 2 into smaller pieces. So imagine I'm slicing it into subsquares, like so. And the more squares that I use, the better the approximation that I will get for the volume underneath the surface. So these squares I can label maybe, or the points on these squares that define these squares I can label as x0, x1, x2, all the way down to xn minus 1 and xn. And then, of course, y0, y1, y2, all the way down to y sub m minus 1, y sub m. And then the width of these squares would be delta x. Okay, the heights of these squares would be delta y. If I can imagine that x0 is starting at some a and xn is starting at some b, then I would have that delta x is going to be b minus a over n. And then I can start each x at a and then add multiples of delta x to get the other x points. The delta y, if I think of y0 as being c and then ym as being d, is going to be d minus c over m. And then I can think about the y's as starting as c, and then I'm adding multiples of delta y. So k delta y. So if I want to approximate the volume underneath this surface, then I want to take the volume of one of these rectangular prisms. The volume, I'll call that maybe delta v, okay, is going to be the height of the function f of xy for some particular x and y inside that rectangle, delta x times delta y. So I want to take a sum of those. So this ends up being a sum. That sum is over j's and k's. And I'm going to sum f of xj yk delta x delta y. And then there's choices for which point within each square that I might want to pick. I could go ahead and always pick like the lower left-hand corners of these squares. I could imagine a scenario in which you're always picking the upper right-hand corners of these squares. Finally, I could maybe perhaps choose midpoints of these squares. So in any case, it doesn't really matter which point I choose within the squares if we're letting the squares themselves, in this case, get smaller, okay, in both width and height. So I could choose any point within the square. So a lot of times we write x of xj star and x and yk star, meaning any point that's within these squares. I keep saying squares because they're represented on this graph as squares, but they could be rectangles of width delta x and height delta y. So if we sum up all of those volumes that correspond to each one of these rectangles, then we would get an approximation of the volume underneath the entire surface. So formally, we let our rectangle go from A to B in X and C to D in Y. And then we divide our larger rectangle into subrectangles of width delta X and height delta Y, so that we have this delta A, the area of each one of those rectangles, which is delta X times delta Y. Then we need to choose points XK or XJ and YK, okay, that are indexed along the X or the Y axis. Okay, so we're going to choose points XJ star within the square and YK star within that rectangle. And then we can define the double integral as a double sum over f of xj star yk star delta A, where delta A we're thinking of as being delta X, delta Y. And then this sum runs from J equals 1 to M, and then J equals 1 to N, and K equals 1 to M. And then we need to take a limit as N and M go to infinity. Okay, what will happen then is that delta X and delta Y will go to 0 in this case. Okay, that will mean that delta A will go to 0. Okay, so that means that we have these infinitely thin rectangular prisms that we're using to estimate the volume underneath the surface, and that'll give us the exact volume underneath the surface. So the integral represents the net volume between the surface and the xy plane. And so that is the definition of the double integral, which, if you remember the definition of a single integral, it's very, very similar, except for instead of finding the area under the curve, we're finding the volume under the surface.